Hello, everyone. This is my first time speaking at a TLA Plus community event, so thank you, the organizers, for allowing me. Today, I'm going to be talking about some research work that I did during my PhD. We titled it Model Guided Fuzzing of Distributed Systems. It was joint work with Ege, Butchu, and Rupak. Um, um, I'll start a bit about me, and then we'll get into the details. I'm currently a postdoc at Max Planck Institute in Germany, working with Rupak Majumdar. We're trying to build model checker. It's exciting. I recently completed my PhD. My PhD title was Automated Testing of Distributed Protocol Implementations, a topic that I think everyone in this audience will relate to. During this work, we came up with a bunch of techniques, some for unit tests for distributed systems, and we were able to publish that. And also a bit of work about trying to use reinforcement learning to guide exploration. And this was published last year. And a third piece of work, which I'm going to talk about today. Uh, as some context, well, I discovered TLA Plus in my master's, and I've been writing models and running the model checker on TLA Plus ever since. So I'm excited to speak here. And minor detail, I'm on the job market and I'm looking for next avenues. So, about today's topic, I'll give a brief background on what is traditional software testing and then relate to distributed systems. So, you have a program and you want to test this. So, and there's a bunch of inputs that you can give to this program, and you pick a random input and you feed it to the program. You do this many times. And the goal is to find a particular input such that the program behaves badly and you found a bug. Now, this is just random testing in a crux. You can do something better. You can, instead of just feeding the input, you can measure some coverage information on the program, for example, line coverage or branch coverage. And you use this coverage information as feedback to generate more inputs. Again, you do this many times using the coverage information to get better coverage and the hope that you will find more bugs. And this is the basic fuzzing loop that communities have been working on for a long time. And we want to take this loop to distributed systems. So there are many challenges. First, you don't have one program, you have many programs. They're all talking to each other over a network, and you don't even know what you can define as an input to this program. There are some notions. I will explain to the differences and drawbacks and what we came up with. And the second thing is, what is coverage over many programs? You can also just take line coverage, but now does it mean all of them should hit it, or any one of them should hit it, and so on. In this work, we came up with an idea, which is we use the TLA plus model as coverage and see what happens in that. And that's what I will walk you through today. Um, uh, but why do we care about this? It's a bit of motivation that I don't think is much needed for this community, but these are complex protocols, distributed protocols, and their implementations are always buggy. They lead to a lot of downtimes. Some examples that I'm familiar with, and especially the Cloudflare outage. I really liked that article and how they used Raft and how they were able to fix it and so on. Okay, so it's important, and there's been a lot of work that has been put into testing the implementations. So there's popular tools like Jepsen, which use randomized testing to test end-to-end the implementation. This is purely random. You don't get any guarantees. And then on the other hand, you have techniques like PCT and PCTCP, which give you randomized testing, but with some probabilistic guarantee. So these techniques tell you what is the likelihood that you hit a bug, or you will always hit a bug, how many iterations do you have to run to find a bug, and so on. And then there are some frameworks like Coyote, which allow you to write down many of these different implementation testing algorithms. And they also have their own unique algorithms, which use reinforcement learning based techniques. And it allows you to encode any algorithm. And more recently, a work that I believe everyone here is familiar with is Mockit, which is a model-based testing tool where you generate tests from a TLA plus model. I'll focus a bit on this and say how we differentiate from this. And what are the drawbacks that Mockit, using Mockit comes with, and what can we do to overcome them? So throughout the rest of this talk, I'll be using Raft as an example. I believe a lot of you already are familiar with Raft. It's a distributed message passing protocol, meaning all processes talk by sending messages across, and the protocol solves for consensus. So you have three nodes, and they all want to agree on the value. In this case, for example, some random value R1. And they want to do this in the presence of crashes. So if a node just stops responding to messages, you still want consensus. And Raft typically proceeds in two phases. You don't need to know too much of the details. I'll walk you through the protocol in the next slide. There's a leader election phase where you have one leader, and then the leader, elected leader, just says, I'm going to give you what are the next entries, and that's the leader replication phase. So let's walk through the protocol, and at the same time, I'll introduce the TLA model and how we're going to use this. A lot of you might already be familiar with this. So you have three processes, and I'm going to present a snapshot of the state of each process. So this is not the complete state as presented in the TLA plus model, but something that's representative, and we'll use some of these terms later on. So each process has a term, it has a state, whether it's a follower, it's a candidate, or a leader. So initially, a process says, I want to become the leader, it's a candidate, and it sends out a request vote message. So that corresponds to an action, handle request vote request. And other processes respond saying, yes, we elect you to be the leader or not. And this is the leader election phase. So once a leader has been elected, it's going to become a leader. That's also an action in the model. And then it's going to say, here are the new entries and so on. So that's the leader application phase. And there are also actions that correspond to that. But the actual TLA plus model of Raft that was released with the protocol and the implementation comes with these particular actions, which says timeout, become leader, or receive a message. And the message can mean anything. So you have the state, you have actions, and you have a relation that says how to get to the next state. And basically, it's a state transition system. Right. So, okay, just to go back, here's the model. You have some state, you have some actions and relations. Now, once you have this, what Mockit does is it essentially goes through all possible traces, which is what is model-based testing. You can try to enumerate all possible executions from the model and run them. There are some problems with this. One is you have too many executions, which is just basic state explosion, because these models are so many states possible. You will have a lot of executions, and you cannot hope to cover all executions. More than that, even if you have a way to enumerate all possible executions, it's a lot of effort to be able to run an execution that was generated. You need to instrument the particular implementation and be able to control exactly when a message is delivered, which part of code runs. And in Mockit, they do this by annotating parts of code and controlling how which parts of code is running or not. And the third problem with this is that some of the optimizations that implementations include are ignored in the model. So for example, there are snapshots. There are also models that include the snapshots, but generally, for example, models also ignore heartbeat messages. And so there are a lot of implementation details that might never be tested because your model does not include them. So your model has to be very close to the implementation to be able to do model-based testing. Okay, so these are some of the drawbacks, and we'll try to address all of them and see how we overcome. And that brings us to our approach, which is ModelFuzz. What do we do with ModelFuzz? We randomly sample the implementation, not the model, but the implementation using some test cases. And then we're going to execute these test cases on the implementation, get what the execution led to and then run it on the model. So you simulate the model in parallel and use the coverage of the model to generate more test cases. So we have the fuzzer loop from earlier. You have test cases, you run them on the implementation, and similarly on the model to get the coverage and generate new tests. So the mutation part here is a bit hacky. I will come to it later. And let's go into each of these parts and how we do and what are the challenges in each of these parts. First is, as I said earlier, what is a test case? So it's not clear for distributed programs what is a test case. So we define our test case or an input to the program. These two terms mean the same for this talk. So it's a sequence of scheduling choices, and we interleave it with chases, with failures. I'm going to explain what I mean. So this is our test case. You have a sequence of these actions. You can say deliver 5 messages to a process, 3 to another process, crash a process, or start a process, and so on. So this is the input that we randomly generate, feed it to the program. You can ask, why don't we just randomly generate message sequences as inputs so you know exactly which messages are delivered and you can run them on the implementation by controlling the messages. The problem with this definition of inputs is that it's not possible to randomly generate them. Basically, not all inputs are valid. So you can't just come up with a sequence of messages. For example, a non-leader can never send up an entry. So you have to essentially encode the protocol in the input generation process. So it becomes a cumbersome work in itself. So we have a simple definition of a test case, and let's look at how we're going to run this test case. So you have a central node that just captures all the messages, and that's all the instrumentation that is needed. Essentially, each process has to talk to the central node instead of talking to each other. So now the central node can say, deliver 5 messages to P1 and 3 messages to P2, crash a process, start it, and so on. And as I said, we can randomly generate these inputs. The instrumentation is light. You don't need to control per message actions. You just need to control where the messages are going to and when the processes start and stop. And over these input, it becomes also easier to play with different mutations. And by mutation here is you take an existing input, you change it to get a new input, and this new input can give you a new state in the coverage. Okay, so let's run through it one more time, and I'll show you what we capture. So once we deliver messages, we capture events in the processes. So in this case, you can see that after delivering 5 messages to P1, you have some send events, which are, okay, it received a request port, now it wants to send back the response. So you get some events. Similarly, as we go, we collect all these events. Say somebody becomes the leader eventually. So this is what we get out of executing an input on an implementation. So you get a sequence of events. And we're going to use these events to be able to simulate the exact same trace on the model. It's not a one-to-one mapping, but it's a close enough abstraction for us to work with. Now, the simulation part takes these events and converts them to actions. I will come to that. Once you have actions, you can now run these actions on the model. And the goal is to obtain a sequence of states that the model went through by executing these actions. So we saw the model earlier. You have a bunch of actions. Once we run each action, it will go through a sequence of states. We want to get this as coverage information. And there are some challenges doing this with TLA+. We want to be able to do this very quickly. We don't want the simulation process to take a lot of time because this is almost in real time. You're executing them. You want to be able to get the coverage information very quickly. And to be able to do this, the model checker should be able to pick exactly what action to execute, and it should not be a non-deterministic action. So I will come to how we overcome this challenge. And the other thing is we only want to execute the actions that are relevant to the model. Basically, there are some events that don't correspond to actions. We want to drop these. this would be the optimizations that the implementation has, but not the model. Okay, so um, the as I said, we want it to be fast, and one of the main challenges with making it fast is how do we enumerate all these actions to be able to simulate the trace on the model. So here you see the actions as I described earlier. There's a timeout, there's a become leader, and then there's a receive. So the receive here is over a domain of messages, but you can't possibly enumerate all possible messages and then pick that action. So what TLA plus does is it makes it a non-deterministic action. So from a given state, if you pick receive, you have many possible states that you can go to based on the message. And to be able to simulate the exact event trace that we observed, you need to find which of these states correspond to the message that we are talking about. So you need to go through all these states, pick that state as the next state, and then repeat this process. And as you can imagine, the number of next possible states for such an action is too large, so enumerating will take time, and this is too expensive. This is what we observed. It was a bit too slow for us. So what we did is we determinized the model, we resolved all the non-determinism, and we said instead of having one action that says receive a message, we now list all possible messages as separate actions. So TLA plus the model checker now can enumerate all these actions and pick exactly the next one that we want to get to. And yeah, just like as you saw timeouts and become leader before, now you have all possible messages. You can just pick and execute that particular actions. But the problem is it's faster, but it needs a lot of space. So you need to be able to store all these possible actions in memory and pick out the next action. You need to do this beforehand. So if the model and the parameters that you've set it is too big, this can be a problem. So in our case, we had to run them on large machines just to accommodate for the memory. Okay, so I spoke about how to take actions and simulate them on the model, and I spoke about how we get events from executing an input on the implementation, but I did not know how I did not talk about how you map these events to actions. In our case, you write a mapper, and here is where you can introduce abstractions on the implementation to only pick those events that are necessary for the model. So yeah, you only take those actions that you think are needed. For example, heartbeats, you can drop them and you can only pick those messages that the model actually contains. And this process, this mapping is very specific to each implementation. Certain implementations might have more events, more optimizations, but you can make it general. So if you take Raft protocol and all different implementations of Raft, you can generalize to say we only capture these events because this is the model that has only these events irrespective of the implementation. So you can generalize it. And I'll talk a bit about this in future work. Okay, that brings us to the complete picture that about what we do. We take test cases, we execute them on the implementation, we get events, map them to actions, run them on the model, get the coverage information, and mutate. So the only part remaining here is what are our mutations and what do we do to mutate a given input to get new inputs. And the answer is swaps. This is a bit hacky. We don't have an exact idea of why this works, but we observe that it works. Basically, what we do is we swap scheduling choices. So if you had delivered P1 followed by deliver P2, you swap them to say deliver P2 followed by deliver P1. And this is one possible swap that gives us a new input and gives us a new state likely. You can swap crashes. Instead of crashing a follower, you might crash the leader, and this might give you a new state. That's the intuition here. Or you can swap how many messages are delivered per process. So in our experience, these swapping mutations worked out really well. They were able to give us good results on exploring new states. So that completes the picture of what we do. But despite all this, we were not able to observe the results initially. So the graph here represents how many unique states we saw on the model. We tried this, so the green bar, which is quite indistinguishable in this, as pure random. It does not care. It just generates random inputs. And we tried all these different mutation strategies. Still, we did not see any significant gap with random. So we were a bit worried. And we discovered that the problem was something to do with Raft specifically. We were encountering this problem of unbounded terms. What do I mean? So as I said earlier, a term is when processes elect a leader. So what random was doing is it was just crashing processes so that new leaders were elected over and over again. So it was skipping terms. You had term 0, term 1, and it was just getting to higher and higher terms. So this was able to get us to new states, but these new states are not interesting. So we needed to come up with an abstraction over the states that tells us what is interesting. This is different from the mapper. So inside the TLA plus model, you need to be able to capture which are the states that are interesting for us and use that to use that as coverage for guiding the new input generation. So what we did is we bounded the maximum number of terms that are possible in a given trace. This is meaningful in the sense that if you discover a bug, it should be possible to discover it within a certain term limit. Now you can increase this term limit arbitrarily, but we thought this was a meaningful abstraction. And the other thing we did is we merged two different states that only differed in term numbers. So it doesn't matter which term it is for a given, if all the processes are in the same term, are in different terms, but everything else is same about these states, you can collapse them because whatever you are going to see in one, you will also see with the other. So this was another meaningful abstraction that we could do. And this abstraction was implemented inside the model checker, unlike the mapper, which can be external. So we had to go inside the TLA plus model checker to be able to implement this abstraction. And once we did this, we were able to get a good result. So we tested it out on different benchmarks. We wrote a micro benchmark in Coyote, the framework that I initially spoke about. And we tested etcd, which is a popular key value store. Some of you might be aware of this. It's written in Golang. It has a small footprint, but it is hugely influential and popular. And we also tested Redis Raft. This is not so actively maintained, but it was trying to extend Redis using Raft for different processes to be able to run Redis on different processes. It was written in C. We were able to instrument it. And the results are here. So again, it's the same graph. We are observing how many distinct states we saw on the model as we increase the number of iterations that we run. And the orange line is ModelFuzz. The other lines are using traditional guidance measures such as line or trace coverage, and sometimes pure random. So there is no coverage. So with this, what we wanted to show is that using the model as coverage is effective. You can actually get to new and meaningful states. And we observed this across the three benchmarks as well. To compare the different guidance mechanisms, so what we did was we took different processes and combined the line coverage. And if you use this to generate new inputs, do we get to new states? And what we observed is that it saturates way too quickly. So you don't observe any new states. It becomes very similar to random. And with trace coverage, what we saw is that you observe new states too frequently, in the sense that you get to new traces very frequently, but this does not give you better coverage on the model. So line coverage is too coarse and trace coverage is too fine grained. And this is what we observed. And the other thing we observed is that using the model as coverage actually gives you good line and trace coverage. So you don't lose out if you use the model. You get good coverage on the lines or the traces using the model. In terms of bugs, we use the guidance to cover out cover the different states of the model, but does it actually give us new bugs? And the answer is yes. We found one bug in etcd. We filed a GitHub issue. I think they're still working on it. And we found a lot of issues with Redis Raft, but we haven't received much feedback from them. So we don't know what is the cause of these issues, but we did find a lot of issues in Redis Raft. And the other thing is so we show that we are able to find bugs faster compared to other guidance measures. So here you see a table of 14 bugs that we found with Redis Raft, and each entry corresponds to when did we actually find this bug. So we run the fuzzing loop for 20 iterations, meaning we run it for 20,000, so 24 hours each time, and you do this 20 times. And we measure how many bugs we found, when did we find them, and we found that ModelFuzz is able to find these bugs much faster, and especially if these bugs are rare. So in these two cases, we found this bug only once, and only ModelFuzz is able to find it. You can see the trend in the other bugs as well. Okay, that completes our contribution, but where does this fit in? Where does this fit in compared to other work that people have done with distributed systems? There's been a lot of work on modeling, as you might be very well aware. This is the TLA Plus community. So people write models using P, Ivy, or Daphne, or with TLA Plus models. There's a lot of effort that goes into writing these models. But these models eventually are not useful in testing the implementation itself. It's a guidance mechanism. It's a good way to think and test it out if the idea works on the model itself, but all this effort is not useful when testing the implementation. So this work is trying to address this main problem to say that you can use the model to test the implementation and it's actually useful. And that's the real contribution here that we want to highlight. But there are some limitations with this approach. You still need a lot of effort. You need to write the mapper, you need to instrument the implementation to be able to capture the messages, and more than that, you need a model that is in sync with the implementation. You need to maintain the model as well. And the approach is quite sensitive to abstractions, as I showed you. If you use line coverage, which is too coarse, it does not work. If you don't have the right mapper, it does not work. If you don't collapse, as I said with Raft, the unbounded terms, you still don't get anything. So it's a bit sensitive, and this requires a bit of tinkering around to find the right balance. Yeah, those are some of the limitations that we want to address. But going forward, we want a more systematic evaluation of these mutation strategies that we had. So we came up with swaps because intuitively they made a lot of sense, but are there better mutation strategies? Can we use more intelligence means of mutating, for example, using a neural net to learn the model in some sense and tell us exactly what is the next input that can get us to a better state or a new state? So this is an unknown question that is worth exploring. And a more low-hanging fruit is to be able to make this mapping process from events to model actions more automatic. So since you already know the model, since you know exactly what you're testing and what events will be emitted, writing this mapper can be quite automatic, made automatic. And this is something that is a simple next step. And I want to say that with this work, you kind of get conformance checking or testing for free. But as some of you might be aware of, this work that was recently published, they address the specific problem of conformance checking along the similar lines of using a model, running a model on the trace that was collected from the implementation. And I leave a reference to that here. You can check it out. And yeah, these are some possible next steps, and that's pretty much it for me. Thank you for the opportunity, and I'm happy to take questions.
Thanks. Thank you, Srini. What is the test of the implementation? I'm a little confused about what you're inputting into the Raft implementation, and then if you perturb it in any way, like you crash a different node, doesn't the rest of the test completely diverge from the input that you'd had before?
So I don't know exactly what you mean by input. I'll talk about two inputs and maybe this answers your questions. So, okay, first let me move to the slide which defines what is our input. So you see here the sequence deliver P15, deliver P23, so on. This is our input. So this is essentially what we run on the implementation. And perturbing it is the idea. So to be able to perturb it gets us to a new state in the model. And that's the goal. We want to cover as much of the model as possible. Yes, perturbing it completely changes what runs. And that's kind of the idea. We want to get to new state. And the other notion of input that I know is, so you're running etcd, you want to store, it's a key value store, you want to store some keys and values, and exactly what is the key and the value that you want to store. This is also sometimes referred to as the input. In this case, we fix it throughout. We don't actually care about what is the key and the value.
So message 5 is delivered to process 1, and then message 3 is delivered to process 2. We're assuming that messages 5 and 3 were sent by some process, or
Sorry. Yeah, let me go a bit more into the detail. So when I say deliver P15, it means deliver 5 messages that are destined for P1. We don't actually care what is in these messages. And similarly, deliver 3 messages to P2. If there are no messages to deliver, you don't deliver anything.
where did the messages come from?
So other processes send these messages. You store them in this central node, and you keep mailboxes per process. So as and when the messages come in, you put them in this mailbox, and when you get the instruction deliver P1 to 5 messages to P1, you pick the first five FIFO order and you deliver them.
Okay, interesting. I sort of get it. It seems like there are a lot of uh, different things, different varieties um, that you could do on this strategy that this might be a fruitful place to keep exploring.
Yeah. Sorry. Uh, was there a question there?
Srinidhi,
Yep.
is there a difference between model-based testing and model coverage and trace coverage? Because you
Yes.
mentioned line coverage, trace coverage, and I wanted to understand the difference between model coverage versus trace coverage.
So by trace here or line coverage here, again, I should have spent more time on this. What I mean is you use these coverage measures to guide the input generation. So if you see a new trace, you generate or mutate the input. And we are still measuring how many states it sees in the model. So that's one thing. And what exactly is trace is Mazurka with traces. We're using standard reductions and traces to find out what is a new trace.
How do you define model coverage?
So model coverage is the TLA plus model. How many new states did we see in the TLA plus model? So
State versus execution, basically.
yes, it is state coverage. Yes, state versus execution. This is what we were measuring, and we
One,
saw.
one,
Yeah.
one other question, like you said that when you are going from implementation action sequences to model, you
Mhm.
want that to be fast.
Yes.
Why?
So we we randomly generate inputs and we run them on the implementation. And with the standard fuzzing loop, you want the coverage information to generate new inputs. So if this process is slow, you just don't do as many iterations. This is an optimization, essentially. It's not a necessary feature. So if you run an input on the on the implementation, and now you want to simulate it on the model. If you can do this very quickly, you can cover a lot more iterations on the implementation.
Thank you. I have a next question. You mentioned you find, I can't remember how many bugs in Redis. And so what are the natures of these bugs?
So
And another question is, how are they fixed? Did they affect something, change anything, performance or safety?
so the bug in etcd was not on the code protocol, but in how it was being stored. So there is a default memory storage that comes with the implementation, and this memory storage was not returning the snapshot information correctly. So if it did a snapshot, if it did not have a snapshot, it should never return nil. I think this is one of the specifications of the implementation, but it was not doing that, and we filed a report. I don't think anything has happened on the etcd bug itself. For Redis Raft, the bugs were basically crashes. So it is an unexpected crash. We tried to go through the trace and the crash report to figure out why it is happening. There is some idea, but I don't really know what is going wrong in the protocol. But we did not get any information back from Redis Raft. I don't think it is being actively maintained, but yeah, maybe somebody here knows better.
Lots of questions. Thank you for the talk. It's there's so many cool things in here. So it seems like you mentioned conformance testing at the very end, conformance checking. It seems like you get it for free essentially if in the model when you map the trace, you can basically just assert that the trace actually is valid for the
Yes.
model, right?
Yes, exactly. So what I meant is if you're doing model guided fuzzing, you get conformance checking for free. Yeah.
Cool. And then the other thing, your work is really in the context of etcd. So I was wondering about the kind of the effort that was involved to specialize this to etcd and how difficult it would be to get it to work on a different protocol, different model.
We did not spend too much effort specializing it for etcd at all. It can very well be used for different protocols. We did extend the work to another protocol, two-phase commit, but we did not take any industrial implementation there. But yeah, I would say the work is very generalizable, and that's why in the context picture I said you can plug in any different model or any implementation, and the idea should work.
Got it. Although you've described that you have to, add a state abstraction and things like this
Yes,
to
so
actually get it to perform well.
yeah, so it is quite sensitive to the abstraction. So figuring out the abstraction, you need to play around a bit to know why things are not working. But yeah, I agree with you. That's a limitation of this work.
Okay, thank you.
Hi, I was wondering if you could talk a bit more about your modifications to TLC, like kind of what it looked like under the hood. Did it change the way you wrote the spec? Like, did you define a new primitive data type in TLC? I asked because this sounds similar to a feature that we were considering implementing, which is called like a monotonic reduction, which is trying to like you said, unify or collapse these unbounded states that like are just like a monotonically increasing counter. So I'd be interested to hear more about that.
So we did two things inside the model checker. One is there is a simulate method. We wrapped it with a server to be able to do this real time. So instead of running the model checker, there is basically, you can run it in server mode and it only takes one input trace and gives you back the state trace. So essentially wrap the simulate function with the server. And the other thing is for the state abstractions, collapsing different states. Once it does the simulation, we just added a parameter that you can pass to say for this if this is the state abstraction that I care about, then collapse these states once you simulate. So it's not too invasive, the work that we did, because we did not want to go too much inside the model checker, but yeah, this was our changes. And it's also public. I can share a link to the GitHub repo.
Thank you.
The state abstraction sounds like view or symmetry in a config file. Did you reuse that, or is that a different, do you have a different idea?
So it was not so modular. Essentially, we hard-coded what is the model, and here's the function that is going to do the symmetry reduction. But yeah, fixing this is something that we want to work on. But if you were writing a different model, you would have to just, so we introduced a generic interface state abstractor over the simulate method, and we wrote abstractors for specific models. So you can instantiate different state abstractors based on the parameters passed to TLC in the config.
Got it. What is the relationship between the way that you change tests and the non-determinism of the implementation itself? Like when Raft nodes run for elections, they wait a random amount of time. So you could rerun the same test and get different model coverage, even if you didn't change anything about the tests.
Yeah, right. So let me go to the slide where we capture the events. I said this is not really one-to-one. There is a bit of non-determinism here, but what we observed is that this non-determinism does not, it's not, the results are not too sensitive for this, and this might be a problem, particularly with Raft. This might be a problem with other protocols. If it is more deterministic, then it's better, I would say. But really, we did not observe a lot of variation in the model coverage over different runs. So we were able to do quite well on different. So if you look at the graph for etcd, for example, so you don't see a lot of bar around it, but for Redis we did, because with Redis we did not have a tight instrumentation. There was a lot of variation.
Cool.
Hi, this is interesting work. As the next speaker, this is going to be really interesting to refer back to. I'm sure
Thank
you saw
you.
the title. Anyway, I just wanted to ask, and I'm sorry if I missed this, but for the etcd TLA plus model that you, sorry, for etcd, you had this model of Raft that you used. Did you say which one it was, or did you write it yourself? Because there are a couple of existing Raft models, including one specifically for etcd, and I'm wondering if you used this or I don't know.
So we used the Raft TLA model written by the author of Raft. And I think there have been a lot of extension, adding membership changes, adding snapshots and other stuff. And we did not modify it too much other than adding snapshots, which is just another state variable. You keep track of this based on snapshot actions. But in the end, we did not use this as well. So I would say the model that was written by the author of Raft, and it's public. I can also share the link for that.
Well, sorry, can I just follow up really quickly? Are you aware of, in the etcd Raft source tree, there is a TLA plus model that is specific to etcd Raft? So were you aware of this? Sorry.
No, I was not aware of this, but I am on some pull requests. So I will quickly take a look and we can sync on this. It would be interesting to run on that specific model for etcd.
Cool. That was my next question. Do you think it's interesting? Thank you.
Yeah.
Thank you. Just one more question. In your PDF file, I saw the last sentence, right? You mentioned that this you have 13 actually previously unknown bugs in etcd and the Redis. Then moreover, 4 of the new bugs could only be detected by model guided fuzzing.
Yes.
Does that mean, what does it mean? You mean if you run the application, there's no way you can reproduce the bug, or you can show the bug?
No. So that sentence is in the context of the comparison table that I showed you. So if you run the same implementation using different guidance mechanisms, we were able to find some of these bugs, although they were later. And in the interest of novelty, we wanted to say that look, we can also find some of the bugs that are not possible to find using other guidance mechanisms. And when I say 12 new bugs, there is Mocket and there's also another work, Mallory, which uses some reinforcement learning guided approaches. And we wanted to differentiate to say these are bugs that were not found by either of those techniques, and we were able to find them.
Yeah, and one more question. So we've just talked about different specifications for a certain system like etcd, Redis. To what degree can your technique ModelFuzz here be used to actually come up with a specification? If you don't care about bug finding right now, because you don't have a specification yet,
Yeah.
so we
So,
considered.
so we did try this very briefly in the following sense. We took a very coarse model, basically, okay, we want to just track which processor started and stopped. And then this is essentially predicate refinement or abstraction refinement in the academic sense. Yes, it was useful and the technique we used was you run the different guidance measures and see model coverage. If all of them are saturating, then your model is too coarse, and you can start adding more and more variables until you actually see a difference from, say, random or trace or line coverage to know that this is actually useful. But again, this it's a lot of knowing about the right intuition. You can introduce variables in the model that are not really meaningful and still get good coverage, but it should be somehow, it should conform to the implementation. So as long as the goal is to actually get the right model, I think this approach works well.
Then, a related question. You mentioned QL learning in Coyote.
Yeah.
There's also preliminary implementation of that in TLC. The problem with that, I think, is related to what you said about the abstraction function. So in theory, and I wonder if you made the same observation, in theory, on paper, it looks nice, it works fine. But then for real system, it's very hard to find the right abstraction function for the QL learning. Otherwise, it will just generate states where they increase the term, for example. So
right. Yeah, sorry. Please complete your question.
What are your approaches to guiding the users to find the right abstraction function?
I don't think anything here is general enough. So on the RL part itself, we have a separate line of work where we showed improvement over what is in Coyote, and there the idea was to be very fine in the abstraction, but still guide the reinforcement learning using high-level predicates. So you can be very fine in how you define the states, but if you start giving RL rewards only if it satisfies your predicate, you can cover a lot of the state space which you are interested in. Now, the question just shifts from finding the right abstraction to what is the right predicate. So this we found to be easier to answer. For example, with protocols, you can say, I don't care about unbounded terms. I only care that there is at least one candidate, or there is at most. Yeah, you can define these higher level predicates, which are much easier to reason about and use this for guiding. So we found in this is a separate line of work. But for this work itself, finding the right abstraction, yeah, it's a balance. I don't think I can say anything general that applies to all of the protocols. Just that this unbounded terms, it would be common to all protocols. So there is some round mechanism. You want to bound the number of rounds that you see, and you only care about observing different and unique behaviors within these rounds. Say, for example, you can define abstractions that say in a trace I always want to see a commit, or something like this. I don't know if that fully answers your questions. I was a bit vague.
Yeah, no, thank you. Makes sense.
Yeah.
Any other questions? No? Nope. Oh, yeah.
Would it be fair to say that a good guidance for your abstraction function is that it should make your state space finite, like maybe enormous, but finite?
I mean, the models themselves are still finite. So TLA plus needs you to define parameters and so on. I would say finite only on certain variables, not on all variables. This would be a more general statement that I agree with.
Thanks.
Last question.
Yeah, really quick. Thank you for all the answers. Just one more question. So how long did you, how did it take you to do all this work? And like, suppose you, even the last version, whatever you finalize your model and runs, like how long, overall you run all of these things to find 13 bugs or,
So for this table alone, we ran for each guidance measure for 24 hours. So, and we do this 20 times. So we measured, but we ran them in parallel, so it was much faster. The whole experiment setup took about 3.5 days.
And then the 3.5 days finished, you find all 12 bugs. Including, all the bugs will come out together. Okay.
Yeah.
And then how many, right, the last try you did this, but how many like different other tries, over, I don't know, 3 months, you get all these ready?
This is just the final experimenting part, but the
I understand.
instrumentation and so on. I think we took about 3 weeks of work, running it many times to actually get the final result and fine-tuning. If there were bugs in our implementation, we had to fix it and so on.
I see. And then how long did it take you to do the implementations?
I would say a few months, but now that we figured a lot of it out, adding a new implementation or a model is a few weeks worth of effort.
Okay, thank you very much.
Okay, I guess we answered all the questions. Let's thank our speaker one more time.
Thank you.